So if there's a website, I can give my email. Actually, let me just write it down here.
Zahid, you might want to, Jabran, you might want to be a little careful because I don't know if you want to get hundreds of queries from.
I don't anticipate 100 people watching this.
Okay, fine. I'm just telling you right now. The potential audience is in the hundreds.
Yeah, well, look, I would be thrilled if 100 people are watching this and be happy to answer those questions. So is this being recorded now?
Yes.
So if you are watching at home, you're welcome to email me with any questions.
See what a nice guy is.
Very, very nice guy.
Okay. So are you guys getting through these problems? Do you need more time? A little more time? Looks like you're plugging away.
Did you get this one? This was simple, yeah? Lambda max equals 0.0029 divided by T in Kelvin. So which formula would you use for the second one? Stefan Boltzmann. So J equals sigma T to the power 4. And what equation would you use for the third one? Assuming it's a spherical object. It's 4 pi r squared times the previous thing. And 4 is the interesting one, right? 4 is quite interesting. So what happens if you keep the surface temperature the same but the radius doubles? That's just a number, right? I mean, 4 pi r squared times sigma T4. So if you double r, what happens?
Give them a second, maybe they're still working on it. Okay, so I'm going to cut you guys off just because for the sake of finishing today. The first one's straightforward. What was the answer? I didn't actually work these out. So. Anyway.
What's the answer, someone?
R times 10 to the negative 7 meters.
Okay, so that's 500 nanometers, right? Very good. That sounds about right. The second one, Deanne, what did you get?
6.406.
Right, that's ergs per second, okay? So you should put units on these so you have the numbers are meaningless without the units. Okay, the third one, did you guys get a chance? Were you able to calculate that? Oh, you don't have a calculator. Okay, you should bring one though in the future because. Okay, yeah, no problem. But just because you probably want to get like the practice of doing this fast because that's what you guys are gonna have to do in the exam. Okay. So Arnold, do either of you guys have answers?
No, I don't like the units. Or centimeters.
You don't get the units?
Oh, no, can we express it in joules and that's SI units?
You can. There's nothing wrong with that. That's right. We initially had said we should work in SI units, didn't we? Okay, I apologize because the first meeting we had said that. And this is again what I was saying before. Astronomy uses CGS, centimeters, grams, seconds, instead of MKS. So that's why I got confused. In the future, I'll do it always in SI. Unfortunately, though, I don't know. This constant now is given in, you see these units, CGS. So for now, let's work with
Just
CGS.
Google it later, I guess, yeah.
What's that?
Just Google it later.
Yeah, or I can send you an email with what sigma is in MKS. So I apologize for that. The bottom line is this ends up being the luminosity of the sun because this is sun's temperature and this is the sun's radius, okay? And so that's something like 2 times 10 to the 33 ergs per second, I think, if I remember correctly. That's the number. So if you plugged it into the L equals 4 pi r squared sigma T to the 4th equation, you should get that. I think it's 10 to the 33 watts or something, or 10 to the 30 watts. No, 10 to the 27 watts. 26, okay, yeah. Because the 10 to the minus 7 conversion. That's right. So I said there's 10 to the 7 ergs per watt, or per joule, right? actually has some conceptual work, but it should be straightforward, right? If you double the radius, the total energy emitted, the luminosity is going to go up by 4, right? Because you're taking the surface area of the object. But what happens if you double the temperature? 16, right? That's a remarkably larger number because of the t to the 4th dependence. So always keep those dependencies in mind. Okay, now the next thing we're going to talk about is the inverse square law, okay? And this is the inverse square law for brightness. This is how, you know that if you're standing really close to a light bulb, it looks really bright, right? And as you walk further and further away from that light bulb, it looks dimmer and dimmer. Now the question is, how much mathematically is it dimming, right? And the answer is given by this equation here. It's dimming as the square, inverse of the distance, squared, right? So if you double your distance between an object that's emitting, you're going to 1/4, 1/4 the brightness that you observe. Okay? This equation, this is a very straightforward equation. You guys should be very familiar with this because we've talked about inverse square laws before. So the mathematics and the ideas of how, if you double something, you get 1/4, or you triple it, you get 1/9. That should be clear to you because we talked about that in gravity, for example, right?
This is really straightforward, right? Like, suppose you had the sun sitting inside a sphere of radius r, right? So it's emitting its luminosity worth of energy per unit time inside that sphere of radius r, right? So if you double the radius of that sphere, its surface area is going to be 4 times. But that same amount of energy is still hitting that sphere from the inside. So, basically the surface of a sphere.
Right, I think that's exactly right. There's a 4 pi here because what you imagine is the sun's emitting that radiation on a sphere, and the amount of radiation is conserved. So the total amount of radiation stays the same. But as that sphere moves out at the speed of light, right, that radiation is spread over a larger and larger surface, right? And that surface, the total is conserved, so that means that the radiation must be spread more thinly by the surface of that sphere, right? So if, for example, you were at the surface of the sun, the luminosity would just be the luminosity of the sun. The brightness would just be the luminosity of the sun. As you start to move away, it gets dimmer and dimmer by this amount, right? By 4 pi d squared. So if you further you move away, as the square of the distance, it decreases. Okay, so this is, I think, a very interesting question and worth something for you guys to think about, and something I think you guys should discuss with each other. This one I doubt you're going to have. I hope you probably won't have an answer right off the top of it. Maybe you will. But anyway, so what other phenomena have we discussed, physical phenomena, or do you know of that exhibits this inverse square law? And is this coincidence, or is there a deeper physical reason for inverse square laws? And what do you think this reason could be? So you guys can discuss with each other.
Oh, come on. At least one other phenomenon that follows the inverse square law. We were talking about.
Right, that's one. How about another one that we've actually discussed? Gravity, that's another one, right? Good. So let's just say those two. Let's just take those. There's plenty others, actually. Let's take those two for now. Now, do you think it's just coincidental that this happens, that they follow this inverse square law? Or do you think there's probably a deeper physical meaning? I mean, you probably know there is, because I wouldn't be asking this question if there wasn't, right? So what do you think that could be? Why do you think that happens? Just look at this equation. Why is it d squared over here?
Area has units of.
So it's area.
Yeah, so that's a hint. That's in the general direction. So it has something to do with that. I think just think of brightness. What is it in brightness that makes it follow this relation? I'll just give you the answer because it's hard to put the words in. Actually, I have to copy this from Wikipedia because they were much more eloquent than me. So first of all, in addition to brightness, gravitational force, electromagnetic force, and sound intensity, right? The way sound, how loud something sounds, they all drop off as the square of the distance. The reason is because we live in a 3-dimensional spatial dimension.